Welcome everyone. So welcome to the 25th Hintze Lecture here in the Department of Physics at Oxford. Welcome to those of you in person and those of you online. I'm Stephen Smart, in case those of you don't know me. I moved here to Oxford in October 2022 to take up the Philip Wetton Professorship in Astrophysics. Generously endowed by Philip and Rose Wetton, who've just been on the phone to me and can't make it. They're stuck beyond the ring. They're not even at the ring road, and they think it would take them 2 hours to get here, so unfortunately they're going to have to cancel them and won't be with us tonight. This is the 25th talk in the series. I'm delighted and honoured to be presenting my first Hintze lecture. It's my pleasure to thank Lord Michael and Lady Dorothy, who are with us tonight, for their fantastic support for science and astrophysics here in Oxford. The Hintze Charitable Foundation funds and supports not just this lecture series to bring us together and hear from world-leading researchers, and we have another one with us tonight. But in addition, it funds supports around 6 early career researchers at any one time, postdocs and students, to work on the latest astronomical surveys that really do have a global scientific impact.
So I took over as director of the Hintze Centre this year from Roger Davies, who unfortunately Roger and his wife Yo can't be with us here tonight. They're in the Austrian Alps with some friends. It just wasn't possible to get everyone together here in May, but Roger will be back with us in the autumn. I'd like to thank Roger for his enormous help in handing over the Hintze leadership to me over the last few months. I'd like to thank, I'm sure he'll be watching this recording. He had a fantastic and influential scientific career here, and we will celebrate that on the 30th of May here in the department. So Roger and Yo, thank you very much for the guidance and help in settling here into life in Oxford. So on to our lecture tonight. It's a pleasure to welcome our speaker, Professor Matthew Colless. Matthew is a distinguished professor at the Australian National University. He's spending some time here in Oxford. He is formerly a director of the Research School of Astronomy and Astronomy and Astrophysics at the ANU. He's a world-leading scientist in the field of astronomical instrumentation and large-scale surveys of the sky, which we'll hear about. He did his undergrad degree at the University of Sydney and a PhD at Cambridge. He worked at the University of Durham, Kitt Peak National Observatory in the US, and was director of the Australian Astronomical Observatory for 9 years. Throughout his career, he's pioneered the development of novel instrumentation and focused on how to survey the sky in its broadest sense, simultaneously capturing light from hundreds of galaxies, thousands of galaxies, tens of thousands, and now we're at the tens of galaxies in these surveys. An early groundbreaking project, a UK-Australian collaboration called the 2DF Galaxy Redshift Survey at then the Anglo-Australian Observatory 20 years ago. That really set the benchmark for every astronomical survey to come since. Innovative instrumentation, meticulous data analysis, measurement, working with theorists. That was a groundbreaking survey project. Matthew was one of the leaders of that project, and many since. He's a fellow of the Australian Academy of Science, an honorary fellow of the Royal Astronomical Society, and in 2023, he was appointed an officer of the Order of Australia for distinguished service to scientific research. He's also known for his generosity to his collaborators, his teams, and junior researchers whom he has mentored, and he's also quite a good public speaker, which you are about to find out. So Matthew, welcome.
Thank you very much. Well, thank you very much for that warm welcome. I hope my sound is good. Please tell me if it's not. I am very glad to be in Oxford. I'm very happy to be here for a year on sabbatical, concentrating again on research after nearly 20 years leading observatories and research schools and having a sliver of time for my research. It's nice to be able to focus on it again fully, and it's wonderful to do so in the incredibly invigorating atmosphere here at Oxford. So this is a public talk. I'm going to be talking about what we do and don't know about the universe and explaining a little bit about how we know it. Now, clearly, I'm not going to fit everything we know about the universe into the 50 minutes I've been allocated. And so this will be highly selective, and obviously it will focus on things I'm particularly interested in. I am trying to keep this at the level of a public talk so the several hundred people online can follow it. But I also know that I've got many astronomers and physicists in the audience. And so I'm trying to do a few deep dives in a couple of areas where I hope my general public will follow along the sense, even if the details escape. And at the same time, I hope my more expert listeners here in the hall will make do with the Cosmology 101 while I am sharing that with the general public. If you're only satisfied half the time, I'll call that a win. Okay, so let's talk about the universe. What do we know? More importantly, what don't we know? And how do we know the stuff we know? And I guess, how do we find out the stuff we don't? So here is a potted summary of the last 10,000 years of cosmology. The point of this little cartoon is simply that the basic questions don't change. We are still asking, as we have always been asking, where the hell did it all come from? The difference is that now, instead of looking at the night sky with wondering eyes, we're looking at it with giant telescopes, with satellites. We're looking at it in the whole electromagnetic spectrum, plus neutrinos, plus gravitational waves, and all the rest. We've got a much better view of the universe. We've got much sharper questions about it. And we even have a little more understanding. And so the what the hell we don't know is now much better defined than it used to be. But we still don't know a lot. So cosmology, of course, is a study of the universe as a whole. Observational cosmology, the sort that I do, which I'll be talking about tonight, means looking at what's there in the universe to see what's there and how it might be explained. And it's important to remember that in many ways, cosmology is as much like history as it is like physics. There is only one universe to observe. We have only one historical universe, one cosmic time to look back at. We're fortunate, unlike the historian, in that we can actually look back and at large enough distances see the universe as it actually was in distant time. It's like being on a distant planet and having a giant telescope aimed at the Earth and seeing historical things as they come by you in real time. And that's an enormous advantage, but we are limited to that one universe. The idea is that we're trying to see what's behind the appearance of things. In this famous illustration from the Flammarion Encyclopedia, it's the appearance that we're looking past and beyond, past the set curtain and into the machinery behind the universe. Now, our view of the machinery is a little bit more sophisticated. So our equivalent of that is this schematic model of our cosmology, of the formation and the evolution of the universe, starting with a big bang, inflating, having the cosmic microwave background, the dark ages, the formation of the first stars, the formation of the first black holes and active galaxy nuclei, reionizing the universe, giving us modern galaxies, which then evolve over most of cosmic history to form the structures we see today, including everything from the largest clusters of galaxies down to you and me. This is our fundamental model. Now, many things about this model are a lot less certain than it might seem. The model itself is really only about 100 years old. These are the two founders of modern cosmology. Albert Einstein provided us with the theory of general relativity, which is the framework on which all of modern cosmology is built. And Edwin Hubble made the critical discovery of the expansion of the universe, which, as you'll see, is still completely central to everything that we do in modern cosmology. So let's talk about that expanding universe. This is a fact. The universe is expanding. So what does that mean? What it means, very simply, is that every galaxy is moving away from every other galaxy. And galaxies twice as far away are moving apart twice as fast. Nice and simple. What is it expanding into? Well, it's not expanding into anything. This is where it gets a little bit more tricky. Space-time is actually stretching everywhere, so that the universe as a whole is just expanding. It's big, it's getting bigger, but it's not getting bigger into anything else. And it has to be remembered that not everything is expanded. You and I aren't expanding. Our solar system is not expanding. Our galaxy is not expanding. Our local cluster of galaxies is not expanding. Things that are held together by other forces or by enough gravitational matter are not expanding with the universe. they've separated out from the overall expansion of the universe. So only things on very large scales are following this. Cosmology is the study of things on very large scales, so we'll stick to that. Why is the universe expanding? Okay, so now we're getting to the point where we're having to give less satisfactory answers. The basic answer here is because that's how it came out of the Big Bang. It came out very hot, very dense, and very highly ordered. And we're not entirely clear on why that is. Ever since, however, we do understand what's been going on. It's been very simple in very broad view. The universe has been expanding, diluting, cooling, and becoming less ordered. That's the history of the universe in a sentence. Let's get to the really interesting part where it gets quantitative. How fast is the universe expanding? Well, the rate of expansion today is called the Hubble constant after Edwin Hubble and is written as h0. H for Hubble, 0 for today, redshift 0, present day universe. And it's conventionally measured in units of kilometers per second per megaparsec, which is one of the sillier units in our field littered with silly units, because of course, kilometers per second per megaparsec is simply inverse time, right? It's really a relative expansion rate. And the reason that we use these somewhat silly units is because the thing we're doing all the time with the expansion rate is saying, how fast is that galaxy 100 megaparsecs receding from me? And it's a lot easier to remember to multiply by some number than it is to invert a time and do the relative expansion and all the rest of it. So here's the number. The Hubble constant is around about 70, around about 70. But that around about, that approximation glosses over a major crisis and opportunity in modern day observational cosmology, which may just offer us a really important clue to fundamental new physics. So let's get into that in a big way. Let's really take a close look at what the expansion of the universe really means. First of all, how do we measure it? The way we measure it basically is by using some sort of standard, typically standard candles or standard rulers, although the gravitational wave people are also going to bring us standard sirens in due course. A standard candle is simply something whose absolute brightness you know its true brightness. So when you put it at some distance, you can predict from its measured apparent brightness how far away that was. Very simple. If it's twice as far away by the inverse square law, it's 4 times as faint. Standard ruler, same thing. If you know how big something truly is, you can put it at a distance, measure its apparent size, its angular size, and say how far away it is. It's twice as far away, it'll be half as big, apparently. So these are the basic tools. Now, when we are constructing the measurements of the Hubble constant, we are currently using a 3-step distance ladder. There are 3 steps to measuring the modern Hubble constant. The first step is geometry. We're using the fact that orbits and Kepler and Newton are very simple, straightforward, we understand them, and if we have the right sort of circumstances, then we can use the parallax, or we can use detached eclipsing binaries, or we can use water mazes orbiting in nice Keplerian orbits and do simple trigonometry and figure out distances. And that calibrates everything else for us. That's the basis on which everything is anchored. The second step of the ladder is to use Cepheid variable stars. These are variable stars whose brightness is linked to their variability. The period of their variability, if it's longer, the star is brighter. If it's shorter, it's fainter. If we can calibrate that period luminosity relation, then we've got a standardizable candle in Cepheid stars. And these are good at intermediate distances, stretching out through our galaxy, neighboring galaxies, and indeed to the nearest galaxies in which we detect supernova. Exploding stars, another type of standardizable candor. These are stars that go bang in a way which, again, the duration of the light that they emit, the period of their curve, is in fact related to their luminosity. And so we can, again, standardize them and use them as a standard candle for measuring distances. So here's the modern 3-rung extragalactic distance ladder. This is the most bang up-to-date one from the Shoes collaboration. At the bottom, you've got the geometric anchors. And so down here, let's see, Down here, you've got geometry giving you real distances, and you calibrate Cepheid magnitudes from it. Once you've calibrated them, you can use them to calibrate supernovae, and then the supernovae give you distances which you can compare to redshifts. And now you've got a Hubble diagram. The thing in the top right, that's a Hubble diagram. You're measuring redshift, recession velocity, the rate at which things are moving away from you in the universe against a real distance. And now you can compute that rate, so many kilometers per second per megaparsec. And when you do that, the answer you get with the best methods we've got available today is 73.0 plus or minus 1.0. So this is good, not quite to 1%, but 1.5% or thereabouts. And this is our best distance ladder estimate of the expansion rate of the universe today. Now, let's switch tack. There's another way of measuring the expansion rate. And that's not to look at very nearby things, as we did with the distance ladder, but to go to essentially the other end of the universe, or at least the other end of time, and look at the relic radiation from the microwave background. We can now measure the microwave background radiation using satellites, in particular the Planck satellite here, launched by ESA, with exquisite precision. The fluctuations in the microwave background are of order 1 part in 10 to the 5, right? And we're measuring these incredibly precisely. And we get a map like this of the temperature fluctuations over the whole sky of relic radiation from the Big Bang. And the red points there are the slightly hotter bits, and the cold bits are slightly cooler. Now remember, they're hotter and cooler around about 2.7 degrees above absolute zero. So hot is very definitely relative here. And they're only hotter by a few parts in 100,000. These are exquisitely precise measurements, beautifully, beautifully done. This is the 3rd generation of these satellites, and we are now measuring these fluctuations with exquisite precision. Now, the way we deal with that is we do a statistical analysis of the fluctuations. We basically look at how big the amplitude of the fluctuations is as a function of scale. So this diagram is showing you angular scale with large scales on the left and small scales on the right. It's showing you the amplitude of fluctuations in a form called the power spectrum. And the red dots with the error bars are the measurements from Planck, and the green line is our best fit standard cosmological model, which has 6 parameters. I keep holding up one hand, then I have to remember to hold up a finger as well. Just 6 parameters, and you can fit all of that. Okay, now let's just go back. This big bump here at around about 1 degree, that's clearly the strongest fluctuation, and you can clearly see that there. There's clearly a scale. Those little dots you see, the speckling all over it, that's on a 1 degree scale, and that is that peak you're seeing there. And that's produced by the baryon acoustic oscillations in the early universe. Let me unpack that a bit. Baryons are just astronomers' way of saying ordinary matter. The baryon acoustic oscillations in the matter distribution result from pressure waves in the highly ionized plasma in the very hot early universe, which freeze out on one particular scale when the universe cooled enough to become neutral, and the photons that were doing the ionizing of the plasma can freely travel through the medium. These frozen sound waves give us a bump in density on a scale of 150 megaparsecs, a physical scale of 150 megaparsecs, i.e. about 500 million light-year scale. So this is an enormous scale, but it gives us a standard ruler. Moreover, that standard ruler is imprinted on the microwave background. We've just seen its signature. That 1 degree bump are the baryon acoustic oscillations. But it travels down through time and is apparent in the galaxy distribution as well. So we see a tiny bump, an excess in the number of galaxies separated by a scale of 150 megaparsecs as well. And so we can use that as a standard ruler to get the expansion history. Now, in fact, we've got much more than just the temperature. We now not only have the temperature map smoothed out a bit there to give that red and blue map at the top left, we also have the polarizations of the CMB. And from those, we can also derive a CMB lensing map as well. So in fact, we've got a huge amount of information. And so we're not just fitting those fluctuations in temperature, we're fitting fluctuations in temperature, in the cross correlation between the temperature and the polarization itself, and the lensing. And all of that is fit with this single 6 parameter model. And there it is. Those 6 numbers give you all those curves, and they give us our baseline model for the standard cosmology. Now, in fact, those aren't terribly useful numbers in many ways, particularly when giving a public talk. So we tend to use these other derived parameters, which are just ways of rearranging those 6 numbers. You can take those 6 numbers and compute all of these numbers from it. And of course, the thing that we're interested in here, for now at least, is the Hubble constant. And the Hubble constant you measure from the microwave background using the baryon acoustic oscillations is 67.4 plus or minus 0.5 kilometers per second per megaparsec. So twice as accurate as the measurements from the local distance ladder. And that means you get an age of the universe of 13.80 billion years. So we can now answer a really fundamental question that's been interesting to humanity down the ages. How old is the universe? Well, counting from the Big Bang and using that best fit CMB set of parameters for the standard model, it's 13.80 billion years old, plus or minus 24 million years. What's 24 million years between friends? Blink of an eye. Important to note, this is consistent with everything else we know about astrophysics. In particular, it's consistent with the ages of the oldest stars, which we can derive independently from stellar evolution theory. So H naught from the CMB is coming from fitting the baryon acoustic oscillations in the CMB power spectrum. We get this 67.4 plus or minus 0.5 number. How big a difference does that make? Well, in the diagram here, I'm plotting on the CMB power spectrum, both a model with H naught of 67 and H naught of 73. Those are the red and blue curves. And you will clearly see the stunning difference between the two curves, right? It's very subtle. You can see when you ratio the two curves, which is the cyan line down near the bottom here, that it's just a slight tilt and fluctuation difference. It's really very subtle. It's not a big difference. The data, however, tells us that this difference is more than 5 sigma, the gold standard for having a real difference. So that's the CMB. What about using baryon acoustic oscillations in the galaxy distribution? Well, we can also compute the galaxy distribution. Here's a simulation of the galaxy distribution as it evolves over the history of the universe, forming this incredibly beautiful cosmic web of structures that we can measure by doing redshift surveys, finding the positions of galaxies on the sky and then measuring their recession velocities and their redshifts. And that allows us to make giant maps. And from the giant maps, we can get a huge amount of information. The large-scale structure of the universe encodes a heap of information. It's very, very rich. It gives us information from its geometry, information from the power spectrum shape, information from the bias of where galaxies actually form, and there's information from the growth of structure over time. All of that is encoded into that cosmic web, and we can extract from that using these big redshift surveys. So that's what I've been doing for the last 25, oh no, it must be long, a very long time indeed. Here are some maps. In blue here, I'm showing you some maps of the galaxy distribution. These are now maps that are 20 years old. I'll show you some newer ones soon. But the first of these maps was the CFA Great Wall, the smaller one at the top there. That showed us that there really was big structures out there. It wasn't a fair sample of the universe, but it showed that there was real information there. The 2DF Galaxy Redshift Survey on the left and the Sloan Digital Sky Survey at the top were the first big surveys happening around about 2000, which actually had a big enough volume of the universe, typically of order a cubic gigaparsec, to fairly sample the large-scale structure, and enough galaxies in the sample in order to get statistics which could actually measure things accurately. Remember, the galaxy distribution is preserving a memory of the initial conditions, for example, the baryon acoustic oscillations, on the largest scales. Even while on the small scales, it's destroying that information by forming bound objects, clusters, galaxies, black holes, and so on. The other thing to remember is that the CMB is a snapshot of the structure in the universe at one very specific time, the redshift of 1100, back at the very beginning of the universe, only 300-odd thousand years after the Big Bang. Whereas with galaxy surveys, if we take look at them at different redshifts, we can actually map that structure as it evolves all the way from the CMB down to today. So that's what we've been busy doing. For the last 20 or 30 years, we've been making bigger and bigger maps of the universe. Here's a list of a whole bunch of acronyms which stand for surveys of galaxies. And the thing to point out here really is the size and scope of these surveys. The two things you care about are how much area of sky did you cover and how many galaxies do you have in your survey? And the two numbers after each of these little acronyms are the log of the number of square degrees covered and the log of the number of galaxies. And the purple ones, the first generation, have tens of thousands. The second generation, including 2DF and Sloan, had hundreds of thousands. The third generation, the best we have right now, like BOSS and eBOSS and so on, are of order 1 million. The ones that are happening right now and happening into the future will be tens of millions of redshifts over enormous volumes. And the combination of the DESI and FORMOST surveys, the two at the bottom there in red, will in fact cover more than 3/4 of the whole sky. Another way of looking at it is like this. If you plot the area in X and the density of sources in Y, then the number of galaxies are those dotted lines moving diagonally. And as time has gone on, we've moved out towards the top right corner of that diagram. And so now the most recent surveys happening up here, things like Euclid, 4HS, and DESI Bright Galaxy Survey, and Emission Line Survey, they're right up there over that 10 million galaxy mark. So, things to remember, we're back to the baryon acoustic oscillations. What can we do with them? So the baryon acoustic oscillations map the cosmic expansion both along the line of sight and across the line of sight. You get 2 bits of information with your measurements. It's very valuable because that means that you can measure the BAO as a function of redshift, as time, and get the evolution both of the expansion rate, the Hubble constant as a function of redshift, and the angular diameter distance as well across the line of sight. And that means that with BAO, you can probe both the dark energy and gravity at the same time by looking at that formation of structure. So we've been doing that. The survey that I did after the 2-degree field redshift survey was called the 6-degree field redshift survey. So, okay, not the most original thinker in the universe, admitted. Nonetheless, it did some very nice things. And one of the things it was able to do was, because it was measuring the BAO at very low redshift, it was able to get an estimate of the Hubble constant, which didn't involve using the cosmological model to translate from one redshift down to today. And what we actually found when we measured that Hubble constant was 67 plus or minus 3 kilometers per second per megaparsec. So our number, although it's considerably less accurate, gives the same number as the CMB measurement and a different number to the distance ladder. So we not only have that the CMB gives a different number to the distance ladder, we also have that BAO measurements at low redshift, not just at high redshift, give a different number to the distance ladder. And so we have this Hubble constant discrepancy. We have the fact that the 2 measurements of H0, the 2 best measurements, the Planck CMB measurement and the Schu's distance ladder measurement, are 5 sigma different, 67 to 73, and never the twain shall meet. And in fact, it's not just 2 measurements. You're not meant to read that long list of things. That's a list of papers giving measurements of the Hubble constant. The ones above the dotted line are basically using baryon acoustic oscillations, and they're getting numbers close to the CMB number, which is the little purple vertical line around 67. All the local distance measurements, the distance ladder type measurements, are scattered around the orange line, which is the best distance ladder measurement. That's 73 plus or minus 1. So we really do have a serious problem here. Let's back off from that a bit. Let's talk about the standard cosmological model for a moment. In the standard cosmological model, general relativity relates the mass, the energy, and the geometry of the universe. And it tells us that in units of the critical mass, which is simply the mass, if there was nothing but mass in the universe, needed to keep the geometry flat, i.e. locally Euclidean everywhere, then the sum of the mass in units of the critical density, the energy in the cosmological constant, or the vacuum energy, omega lambda, and the energy in the curvature of the universe, omega k, has to sum to 1. Okay, nice simple rule. In a simple, beautiful universe, since we know there's matter, the most beautiful universe would be where matter was everything, the cosmological constant was irrelevant, it was nothing, and the geometry is flat. 1, 0, and 0. That would make things very nice indeed. Critical matter density, no cosmological constant, geometrically flat. What do we find, however? Okay, here, going back to our measurements from the CMB, we find that the matter density is in fact 0.31 in these same units. Instead of being unity, it's 31%. Not a very satisfactory sort of number. However, there's a get out. This standard model is assuming a flat universe and assuming a cosmological constant. In other words, it's assuming that omega k equals 0, and there's a cosmological constant to make up the difference between the matter and the one that we need to add, everything to add up to. Let's check that. We can take the same data, the CMB data, and check it. What do we find? We find that when we actually allow the curvature to be a free parameter of the model and fit for it, what do we get? We get 0.0007 plus or minus 0.0037. In other words, the universe is damn near flat. If it's not flat, it's doing a very good impersonation of it. We also find that when we look at the equation of state of whatever it is that we think is a cosmological constant, it comes out with an equation of state parameter of -1, which is exactly what you would expect if it really was Einstein's cosmological constant. So it looks as if our assumed model, where omega k was 0 and the dark energy, the thing that's missing, is really a cosmological constant, is justified from the data itself. So combining the data from the CMB and doing the same thing, throwing in the data from the galaxy surveys and from the supernova studies, putting it all in the pot and mixing it up, the best answer turns out to be that matter is 0.31, omega matter is 0.31, omega lambda, the cosmological constant, is 0.69, and the curvature is pretty nearly 0. So it's neither simple and beautiful nor entirely random. It's not as if those were 3 random numbers. One of them is exactly the sort of special number that you might hope would be a physical prediction. The other 2, not so much. Matter's not everything. The cosmological constant is not nothing, but at least the geometry is very flat or close to. And the question is, who ordered that, or why is it so? All right, let's go and think about what the universe is made of. What are the actual contents of the universe? It turns out that from the amount of structure in the CMB and the growth of structure in the galaxy distribution, we can precisely measure the amounts of ordinary atomic matter, the baryons. We can measure the amount of radiation and neutrinos, and we can measure the amounts of dark matter. Okay, I'll have to explain that, and dark energy. So dark matter is the gravitating matter that we see everywhere in the universe. We need it to explain galaxies, we need it to explain clusters, and we need it to explain the large-scale structure of the universe. This is matter that is not interacting with anything else except through gravity. And if you just assume that there's something out there that's gravitating, but which we can't otherwise detect, then everything works a treat, and you can measure the amount of it. And you can measure it separately from the baryons. Second thing, the dark energy. Something is causing the universe to have this cosmological constant. We'll call it dark energy, and we'll need to explain that. But we can measure it from the effect it has on the universe, because it has a different effect on the history of the universe than matter does. So when we do that, here are the answers we get. We find that, as we've said before, omega matter is 0.31, that omega baryons is given by a number there, and the neutrinos are given there. And in fact, we can turn that into a pie chart of the contents of the universe, where radiation makes up a very tiny amount of the total energy density of the universe. All the chemical elements other than hydrogen and helium are 0.25%. Neutrinos are 0.5%. Stars and free hydrogen and helium are around 4%. Cold dark matter is 26%, and the dark energy is 69%. So ordinary matter, when you sum up all the bits that are ordinary matter, only amounts to 4.5% of the total contents of the universe. So within the volume of the visible universe, out to 13.8 billion light years from us, that amounts to about 10 to the 80 atoms, about 400 billion galaxies, and each galaxy has, typically for a Milky Way-like galaxy, about 400 billion stars. So that's 4.5% of the universe. What is the rest? Dark matter and dark energy together make up 95% of the total energy content of the universe. But what are they? What is dark matter? And this is where we have to say we really don't know. You can go online, look in the Physics and Archive, and find an infinitude of papers suggesting what it might be. Favorite candidates are weakly interacting fundamental particles that are simply not known in the standard model of particle physics. This might be a massive particle, weakly interacting massive particle, or WIMP, or it might be a very light particle like an axion. But honestly, we really don't know. Astrophysical searches for dark matter in various forms that might have astrophysical implications, for example, primordial black holes or radiatively decaying dark matter, have come up empty. We've never had a credible detection. Likewise, there have been many tests looking for dark matter in the lab, looking for interactions based on weak or strong nuclear force or something else. We might see dark matter in a lab sometime in the next decade. There are lots of experiments looking for it right now, but we've been saying that for the last 30 years. So it's not clear. So there's another possibility as well. Not only might it be a type of matter that we can't detect or find, it might actually not be matter at all. It might be a modification to gravity, some alternative to general relativity, or some manifestation of our non-existent theory of quantum gravity. Okay, so we didn't do very well with dark matter. Let's see if we do better with dark energy. Nope. If we don't know about dark matter, then we really, really don't know about dark energy, right? All we know is the effect it has on the overall expansion history of the universe. If we put in a cosmological constant, everything kind of works. But that's about it. We don't know whether it's really a cosmological constant, whether that should be interpreted as vacuum energy or something entirely different, because when we try and calculate it, we don't get the right answer. In any case, it is necessarily some sort of new physics. Now, in fact, historically, I've led you to dark energy through fitting the standard model to the CMB and large-scale structure and so on. But historically, the way it was detected was through an extension of the distance ladder. It used to be said by Alan Sandage and others that cosmology was a search for two numbers, the Hubble constant, which we're certainly looking for, and the deceleration parameter. And the deceleration parameter is wonderfully named because the one thing we know the universe is not doing is currently decelerating, it's accelerating. And in fact, this was a big surprise. It was found when people pushed the distance ladder method with supernovae out to higher redshift and found that as they were looking back, the universe was actually accelerating in recent times. Since about 8 billion years after the Big Bang, the universe has actually been expanding faster and faster. If you go back further than that, then the universe was decelerating. It came out of the Big Bang fast, and then all the matter in the universe's gravity pulled it together and slowed down that acceleration. But over time, the matter diluted and diluted and diluted until its gravitational field was no longer able to decelerate it. And the cosmological constant, which is a fixed amount of energy in every bit of volume that you're creating as you expand space-time, is pushing, although it's pushing incredibly weakly, eventually it wins and it starts to push harder and harder and the universe starts to accelerate. And that's worth a Nobel Prize. Here's some of the original data from the 1998 discovery of the accelerating universe. And you can see that the blue bit of that graph is where you're forced to accept an accelerating universe. And the red bit is where you've got a decelerating universe. And the data sort of lie on the blue side of that line. And it was a good thing that there were two teams getting similar results independently of each other, because otherwise they might have had trouble being believed. Now, however, if you do the same sort of data, and again, this is this year's data, they're not bothering to plot multiple different curves. There's only one curve, that's a standard lambda CDM model. And you can see a huge number of data points with teeny tiny errors blown up on that lower diagram, which averaged together give you incredibly tight constraints about that accelerating universe model. And they too imply the same cosmological constant-like effect on the universe. Okay, so that's the history of the universe. What about its future? What's the fate of the universe? Well, there's three ways it can go. One is the way that we think it will go, which is that if things are as they seem and don't change, then it will last a very, very long time, effectively, possibly, sort of even forever, ignoring quantum effects, but a very, very long time by anyone's reckoning. In that case, the universe dies the ill-named heat death, which is really a cold death. The stars burn out, black holes evaporate, all the sources of energy in the universe eventually run down, leaving the universe to cool towards absolute zero, which is a pretty dull way to go. Much more interesting are the two alternatives. So let's think about them. One is the big crunch. Suppose that the cosmological constant ain't constant. Suppose it's some sort of field which is decaying and will go away. And eventually matter takes back over again. And there's enough matter in the universe to bring it all together in a big crunch, and things get very exciting for a finite period of time, and then they don't. That's very unlikely because we know that there's not enough matter in the universe to do it. Even if the cosmological constant went away, the universe would still just keep on coasting away to infinity. Things would have to change radically in order to get that outcome. Slightly more likely, but not very likely, is the big rip, where things get worse. The cosmological constant ain't constant in the way we think either. And in fact, it gets bigger and stronger and stronger and stronger over time, and things exponentiate away to the point where space-time itself is torn apart and you get a big rip. Again, very exciting for a period of time. I think we'll actually hope for the more boring outcome. All right, let's go back to the problem of dark energy. I'm not very hopeful about astrophysical solutions to the problem of dark matter. They may exist, but I'm more optimistic that we might be able to do something about dark energy, even though it's a fundamentally harder problem. And that's because there's two ways in which we can test whether dark energy really is a cosmological constant, modified gravity, or something else. At least two ways I'll be talking about. We can, first of all, measure the expansion history of the universe at very high precision with really big surveys. And the second thing we can do is we can measure the growth rate of structure, again, to really high precisions, again, needing really big surveys. But these are things we can do. Here, for example, those big surveys I've been talking about, the two in red on that slide back there, the ones that are going to measure tens of millions of galaxies, this is how accurately they'll be able to measure the Hubble constant. On the left are all the measurements from baryon acoustic oscillations in the galaxy distribution of the Hubble constant as of now. These are the best sets of measurements. The gray range is the CMB Planck measurement for 67 plus minus 0.5 or thereabouts. The blue is the distance scale. And as you can see, all the BAO measurements favor Planck quite clearly, but they scatter about it. The error bars aren't as good as Planck, etc. On the right, the gray area is the same range of the Planck error uncertainties. And now you can see the galaxy BAO measurements are substantially tighter than the Planck measurements. Galaxies are going to beat out the CMB for this in the very near future. The top survey here is DESI. That's already happening. They have 25 million redshifts in the bag as we speak. Euclid will be launching in July, and MegaMapper is another facility on the horizon. But there's a way we can do even better than just redshifts. We don't have to content ourselves purely with 3 numbers when we can get a 4th number. We can measure peculiar velocities for galaxies. Galaxies don't just move with the expansion of the universe. I have been lying to you this whole talk. Sorry about that. They actually also feel the gravity of the inhomogeneous matter distribution all around them. And they acquire a peculiar velocity, peculiar simply meaning peculiar to them, their individual velocity, which is just them falling into the nearby mass concentrations. And that's in addition to, on top of, the overall Hubble expansion. We can measure those peculiar velocities statistically from redshift surveys. Right? We can use the redshift space distortions that peculiar velocities cause and measure them statistically from redshift surveys, but we can measure them also directly with a peculiar velocity survey. And hey, why not do both, right? This is not either or, this is both and. We can do redshift and peculiar velocity surveys. So this is what the velocity field of a slice through a part of the local universe looks like. Red means moving away from us, blue means moving towards us, and the vectors are the velocity field you derive because, at least in the linear regime, everything is purely a gradient, and so if you know any one component, you can deduce the others. By measuring a galaxy's distance independent of its redshift, we can separate the recession velocity due to the Hubble expansion and the peculiar velocity from the mass distribution. And that gives us additional information because that peculiar velocity is responding directly to the mass. When we do the redshift distribution, we're sampling the density field in a way that's a bit hard to understand. But when we measure a peculiar velocity, we're seeing a galaxy's response directly to the density field. And so it's a very direct and powerful additional measure of what the matter distribution is and how fast it's growing in terms of its structure. And so that can be used to tell us about the matter content of the universe and the nature of gravity. Now, when we do that, when we make measures of the matter clustering, either using the CMB or with the measurements from redshift and peculiar velocity surveys, and also gravitational lensing, although I'm afraid I've ignored that entirely in this talk, then we find that we get, again, another tension. On the right here in this diagram, that little purpley grey sort of colour, that's the CMB measurement of the amplitude of matter clustering. And on the left are all the measurements from weak lensing, from peculiar velocity surveys, from redshift space distortions, from everything else. And you see they all tend to prefer a slightly lower number. Now, this is only at 2 sigma, so this is only a hint at this point, but it's really interesting because if confirmed, it'll be another big clue to new physics in the cosmological model. So what are the big new redshift and velocity surveys that are going on? Well, in the picture on the left, that little bubbly image is our map of the density field around us here in the local universe. That's our best map at the moment using the 60F galaxy survey, the 2-mass redshift survey, SDSS, and a few other things. But the 2 big new surveys, DESI in the north and the Foremost Hemisphere survey in the south, are going to cover 3/4 of the sky between them. DESI is the blue in the diagram on the right, Foremost is in red, and they're going to measure vastly more redshifts and peculiar velocities. DESI, as I said, has already measured 25 million and is aiming for north of 30 million redshifts and about 100,000 peculiar velocities, whereas Foremost in the south, starting next year, will measure more than 10 million redshifts and more than 250,000 peculiar velocities over the whole southern sky. And at the same time, while they're doing that at relatively low redshifts, ESA's Euclid satellite, launching in July, should be able to get of order 100 million redshifts at even higher redshifts. So what are we going to measure in terms of the growth of structure? So here's the growth rate of structure as measured from the DESI survey. The DESI survey is happening on a reconfigured mile 4-meter telescope. It's got 5,000 optical fibers all staring at galaxies simultaneously. They pump out my 2DF galaxy redshift survey, which took me best part of a decade, every month. And if you think I'm not bitter and twisted about that, you're completely wrong. It's spectacularly wonderful. And they're going to be able to measure the growth rate with exquisite precision. The diagram at the top left there shows the measurements of the growth rate at different redshift bins. The black ones are using the redshifts alone, and the red ones are combining the redshifts with the peculiar velocities. You can see how the peculiar velocities really tighten up those error bars, particularly at the lowest redshifts. And the error on the growth rate, you can see in the lower part of that diagram, is 10% or a bit better over this whole redshift range out to 0.2. On top of that, Euclid will be doing something equally spectacular with only redshifts, but with many, many of them, out at high redshift, around about redshifts of sort of 1 to 2. So we're going to have these spectacularly precise measurements of the growth rate of structure, which are going to help us answer many of our big questions. So I'm going to leave you then with both the questions and what I hope is some sort of way forward. There are many wide open fundamental questions in cosmology at the moment. What are the dark matter and the dark energy? Was there an early reinflationary epoch? And how did that happen? What caused it? How did it come about? What is the theory of quantum gravity that really underpins all of this and will allow us to understand these things more fundamentally? Is there some deep fundamental physical reason why the parameters of the universe are the way they are? And did they have to be that way? Or are we in need of another Copernican revolution, recognizing that our universe is just one instance in some vast multiverse, and we're just sampling the bits of that multiverse that happen to be conducive to at least semi-sentient life? Okay, those are the big, hard questions. But there are some sharply posed observational questions which we can move forward with. We can look at what is the origin of that discrepancy in the Hubble constant. This is now sufficiently well investigated by enough different methods and with enough precision that some new sort of physics really seems to be necessary. The question is that new physics astrophysics or is it cosmophysics? Is it telling us something about the universe? Likewise, is there a significant discrepancy in the amplitude of matter clustering as suggested by the CMB as compared to the structural growth and gravitational lensing measurements? And if new data confirms that, as I hope it will with these big new surveys, then the joint H0 and S8 discrepancies are going to be a really powerful new clue for trying to get a grip on what's happening in the universe. So in the near future, these giant new surveys of redshifts, peculiar velocities, and also of gravitational lensing are going to far more precisely measure the expansion history and the growth of structure, and so really constrain the nature of both dark energy and gravity. Where the hell did it all come from? Maybe we'll have better answers next time. Thank you very much.
Thank you, Matthew, for a wonderful talk. I 2DF survey every month.
Yes.
Fortunately, you did it first.
Yes.
Do we have questions from the audience? So we have two runners here. If you would like to ask questions, then please wait for the microphone.
And do feel free to slip away at any point. I do realize we're running a little late.
We got one at the very back. Yeah, you can start at the back and go down.
Thank you so much for this wonderful talk. I've got two questions, if I may. First of all, is there any chance of being able to see if the cosmological constant has changed over time? Is there any possibility to do that? The second question is, could you comment on the James Webb recent observation of these very old
Two good questions. So the first one, the answer is absolutely yes. That's precisely what the growth of structure type measurements and the expansion rate measurements over time will do. They will check whether the trajectory over time of the expansion rate and the growth of structure follows the trajectory predicted by a cosmological constant or whether it's different. And if it's different, it should be able to tell us the difference between different sorts of gravity and different sorts of cosmological constant as well, with the sort of precision we're hoping. So the answer I very much hope is yes. I really do expect we should be able to do that. It may turn out to be exactly as we think now, but we should at least have the precision to distinguish between many of the different alternatives being proposed in the literature now. On the second point, I'm very much of the camp that thinks that the really interesting discoveries JWST is making about galaxies very early in the history of the universe is telling us some more about astrophysics and about how ordinary matter forms into stars and galaxies, and it's telling us about cosmology at this point. I think we've got a lot more to learn about galaxy formation and everything that goes with it. And so I would be very surprised if that turns out to be cosmologically significant, but I have been wrong many, many times before.
Yeah, just below.
Thank you very much for a wonderful lecture. Can you, going back to ground zero, does the period of inflation require signals travel faster than light?
Excellent question. So I didn't really talk about inflation, partly because it's not my field and partly because it would have just made everything even longer. But the answer to that is no. The trick is the difference between things traveling through space-time and the stretching of space-time. Things traveling through space-time have a speed limit, the speed of light, which as far as we can tell cannot be exceeded. Space-time itself can do whatever the hell it likes and can, stretch faster than the speed of light, and indeed is already doing so. There are parts of the universe that are moving out of our visible universe right now because the accelerating universe is taking them out there. So in fact, inflation can indeed stretch things faster than the speed of light, as it were, and indeed must have done so to do what we think it's done, which is to take a single quantum event and stretch it out to form the whole universe in a fraction of a fraction of a fraction of a second.
Thank you. Once again, I'll add my compliments for a superb talk. Could you expand a little bit on the distinction between finding redshifts and finding peculiar velocities? Part of a redshift will involve, I assume, a peculiar velocity component.
Yeah, it does.
So are we also talking about proper motions? How do you distinguish between the peculiar velocity and the redshift?
The thing that you need is a true distance, right? A redshift is really a distance multiplied by the Hubble constant. It's the expansion rate, it's a recession velocity. And it turns out that the observed redshift is 1 plus z. What you observe is 1 plus z cosmological times 1 plus z peculiar. It's a product of two 1 plus z redshifts. And the way you distinguish them is you can get the cosmological redshift if you've got a true distance. And so all our methods for getting peculiar velocities involve getting a redshift independent distance estimate. And we typically do that using very similar methods to those that the people doing supernovae do. We have some sort of calibration. Now, we could use supernovae, they give very accurate distances, but we don't get them in many galaxies. So to do it for many, many galaxies, we use things called the Tully-Fisher relation and the fundamental plane, which are relationships between either a size parameter for the fundamental plane or a brightness parameter for the Tully-Fisher relation, and some parameter, usually a kinematic parameter, a velocity dispersion or a rotation velocity, which isn't affected by redshift. And so if you can measure the kinematic parameter, you can predict the luminosity or the size and then get a cosmological distance. You don't get them very accurately. The distances individually are very inaccurate, but with enough of them, you can beat the errors down and get some statistically very useful results.
We have two questions online.
So there's one question from Ali, which is, could the discrepancy in the Hubble constant be due to a local universe being located in a void with respect to the large structure?
These are all great questions. These are all highly pertinent questions. And the answer is yes, in principle, it absolutely could be. And there are a number of astronomers who think that that's a potential explanation. However, my own work and that of the majority of astronomers suggests that it's not the case. We do live actually in a somewhat underdense part of the universe, that's true, but not nearly underdense enough nor large enough to actually explain the discrepancy in the Hubble constant. So they're sort of right, but not right enough in order to explain it. In fact, the best estimates that I'm aware of can only explain something like a half of a kilometre a second per megaparsec in order to, if we're in the biggest void we think we can, is consistent with the data.
We have another question about the future. Is there any chance of another Big Bang or other external big energy release to be able to affect our universe?
Sorry, just say that again, Anna.
Is there any chance of another Big Bang happening?
Is there any chance of another Big Bang? Well, we don't know what caused the Big Bang, so predicting the probability of another one is a bit difficult. However, inflation, or at least various varieties of inflation, suggest that Big Bangs are actually going off all the time outside our visible universe. There are various varieties of eternal inflation which have a quantum substrate to the universe turning into big bangs left, right, and center, which then all expand away. Whether that's right or not, we have no idea. What we do know is that for the last 13.8 billion years, year on year, the universe has got bigger and we haven't bumped into another universe.
Given the number of surveys that are about to be realized and either start or are in operations, so when do you think that those surveys will produce their results that will give us some idea about dark energy?
Yeah. So the timescale is, I would say, 2 to 3 years for DESI, 5 years for Euclid, and 5 to 7 for Foremost, is my guess. I'm working to make the Foremost one a lot quicker than that, but I'll be conservative here. But it's, you know, a twiddle 5-year timeline. It's not incredibly long. I still plan to be working in astronomy when those results come out, put it that way.
I was about to say, I think you look younger than 5 years from retirement.
I am
so
absolutely younger than 5 years.
To have you back and tell us how these surveys have affected
I would love to do that. I started out doing my PhD when the Hubble constant was not known to a factor of 2. The fact that it is now known to better than 1% blows my tiny mind every time I say it out loud. So I'm really looking forward to being able to say the same sort of thing about the cosmological constant or dark energy before I retire.
Thank you, Matthew.